Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
We look and the world appears. This seems effortless, a passive reception of reality. For centuries, this fundamental human experience posed a profound enigma, a puzzle that occupied the minds of philosophers and scholars, shaping their understanding of the cosmos and our place within it. What is the mechanism by which we apprehend the world around us? Does the eye send forth something into the world, or does the world send something into the eye? This question, seemingly straightforward, held within it the seeds of a revolution in thought, a transition from speculative pronouncements to rigorous, empirical inquiry. The intellectual heartland of this era, the 10th and 11th centuries, pulsed with a vibrant energy in cities like Basra and Baghdad. This was a period of immense intellectual ferment, where the accumulated wisdom of antiquity, particularly from Greek thinkers like Euclid and Ptolemy, was being studied, translated, and debated. Knowledge was a precious commodity, meticulously preserved and expanded upon within grand libraries and bustling madrasas. Within this rich intellectual soil, certain fundamental assumptions about the natural world, including the very nature of vision, remained largely unchallenged, inherited from ancient traditions. The prevailing understanding of sight, deeply embedded in the philosophical discourse of the time, posited that vision was an active process originating from the eye itself. Thinkers like Euclid, in his work on optics, and later Ptolemy, had proposed that the eye emitted rays akin to the beams of a lantern, which then struck objects. These rays, it was believed, returned to the eye, carrying information about the object's form, size, and color. This emission theory, or extramission theory as it is often termed, held a certain intuitive appeal. This explained our ability to perceive objects in darkness when a light source illuminated them. If the eye actively projected its own illuminating beams, then darkness would represent a condition where these beams could reach nowhere or where their returning signal was too faint for perception. This elegant, though ultimately incorrect, model presented considerable conceptual difficulties. If the eye projected rays that traveled outward, how did these account for the immense universe we could perceive? Did these rays travel instantaneously? The immense speed necessary to perceive distant stars, or the rapid flight of a bird, seemed to exceed any terrestrial measure of velocity. Moreover, if the eye projected rays, why did we not perceive our own eyelashes or the interior of our eyelids? Why did blinking not interrupt the continuous flow of visual information? These inquiries troubled the emission theory, suggesting a more profound, intricate reality that the prevailing model found difficult to integrate. The intellectual environment, while abundant in scholarship, often relied on established authority and deductive reasoning. New concepts frequently underwent evaluation through the framework of existing doctrines, and empirical verification, present in some scientific pursuits, had yet to become the universally recognized foundation of knowledge creation. To contest a firmly established theory, one needed more than persuasive arguments. Irrefutable evidence was required, a novel perspective that systematically dismantled the old, piece by careful piece. It was within this intellectual context that Abu Ali al-Hasan ibn al-Haytham, known in the West as Alhazen of Basra, appeared as a truly groundbreaking individual. His intellectual path involved the fundamental redirection of how knowledge concerning the natural world should be sought, rather than a simple refinement of existing concepts. He was a product of his era, deeply immersed in the learning of the Islamic Golden Age, yet his intellect possessed a rare lucidity and an unyielding dedication to observation and experimentation that distinguished him. He recognized that the persistent questions surrounding vision indicated a deeper misunderstanding of the physical processes involved. Alhazen approached the problem of vision with a scientist's mind, a desire to understand the how and why through methodical investigation. He subjected the pronouncements of ancient authorities to scrutiny, testing their logical consistency and their alignment with observable phenomena. His intellectual endeavor was to construct a coherent and verifiable explanation for how sight functioned, an explanation grounded in the physical interaction of light and the eye. This was a radical departure, a call for a new paradigm in scientific inquiry, one that prioritized evidence over assertion and systematic testing over inherited dogma. He sought to build a new edifice of understanding upon the bedrock of empirical truth. His work would ultimately lay the groundwork for a more robust and systematic approach to understanding the natural world, a methodology that would echo through the centuries and form the very foundation of the scientific revolution. He approached the fundamental question of how humans perceive the world around them with the scientist's mind, a desire to understand how and why through methodical investigation. He subjected the pronouncements of ancient authorities to scrutiny, testing their logical consistency and their alignment with observable phenomena. His intellectual endeavor was to construct a coherent and verifiable explanation for how sight functioned, an explanation grounded in the physical interaction of light and the eye. This was a radical departure, a call for a new paradigm in scientific inquiry, one that prioritized evidence over assertion and systematic testing over inherited dogma. He sought to build a new edifice of understanding upon the bedrock of empirical truth. His work would ultimately lay the groundwork for a more robust and systematic approach to understanding the natural world, a methodology that would echo through the centuries and form the very foundation of the scientific revolution. The era preceding Alhazen's groundbreaking work was dominated by a prevailing understanding of vision that presented profound conceptual hurdles. This dominant perspective often termed the emission theory or extramission theory posited that the eye itself was an active participant in the act of seeing, projecting invisible rays outward into the world. These rays, it was believed, would then strike objects and upon returning to the eye would convey information about their form, color, and distance. Thinkers from antiquity, including influential figures like Euclid and Ptolemy, explored the geometry of these supposed visual rays, developing sophisticated mathematical models to describe how they might interact with surfaces and angles. Their work was elegant and mathematically rigorous, providing a framework for understanding phenomena like reflection and refraction. The emission theory, while mathematically tractable for certain geometric problems, struggled to account for a range of everyday visual experiences. One nagging question concerned the speed of sight. If the eye were actively sending out rays, how could we perceive distant objects almost instantaneously? The projection of rays across vast distances for them to return implied a temporal delay that simply did not align with our lived experience. The world appears before us with an immediacy that the emission theory found difficult to reconcile. Furthermore, the theory offered a less than satisfactory explanation for how we perceive the details and colors of objects. If the eye was the source of the visual impetus, what was it about the object that determined the specific quality of the perceived image? The interaction seemed to be primarily one way, with the eye dictating the process, leaving the object's role somewhat ambiguous. Another significant challenge for the emission theory lay in explaining why we could see objects illuminated by a light source, yet perceive darkness when no light was present. If the eye was perpetually emitting rays, why did the presence or absence of external illumination so dramatically alter our ability to see? The theory offered explanations that often involved the rays being strengthened or weakened by external light, but these explanations lacked a clear, mechanistic foundation and felt more like ad hoc additions to an already strained conceptual framework. The very nature of the visual spirit or visual power that was thought to emanate from the eye remained elusive, a vital force rather than a physical entity subject to empirical investigation. This conceptual vagueness meant that the theory, while geometrically useful, offered limited insight into the physical processes underlying perception. Alhazen, or Ibn al-Haytham as he is known in Arabic, meticulously dissected these prevailing notions. He recognized that a truly scientific understanding of vision required a framework that was mathematically consistent, physically plausible, and empirically verifiable. He observed the logical inconsistencies inherent in the emission theory, particularly its difficulty in providing a coherent explanation for the speed and nature of visual perception. His critical examination was a profound reevaluation of the fundamental assumptions upon which their models were built. He understood that the edifice of scientific knowledge must rest upon solid foundations, and that the prevailing theory of vision, despite its intellectual appeal, was built on shaky ground. His intellectual approach was characterized by rigorous skepticism toward inherited dogma, a trait that would define his scientific career. He challenged established authorities, including the philosophical traditions that had long dictated the understanding of natural phenomena. For Alhazen, the act of seeing was a physical process involving the interaction of external stimuli with the sensory organ. This shift in perspective was revolutionary. It moved the focus from the internal, active eye to the external, passive object, and the medium of light that connected them. This conceptual reorientation was critical, as it paved the way for a more grounded, physical explanation of vision, one that could be investigated through observation and experimentation. The problems of his time were deeply entrenched, with centuries of philosophical thought supporting the emission theory. To question it was to challenge a venerable intellectual tradition. The intellectual landscape was one where authority often trumped empirical evidence. The pronouncements of revered philosophers were frequently accepted as definitive truths with little impetus for independent verification. Alhazen's work represented a clear departure from this intellectual milieu. He sought to establish a new standard for scientific inquiry, one that emphasized the primacy of observation and the systematic testing of hypotheses. The challenge was immense to convince a learned audience that a theory accepted for centuries was fundamentally flawed and that a new, more complex, yet ultimately more accurate, explanation was required. His intellectual courage lay in confronting these deeply ingrained beliefs and proposing a radically different understanding of a phenomenon as fundamental as sight. The very questions he posed about vision were, in essence, a critique of the explanatory power of the existing paradigm. He effectively highlighted the limitations of a theory that could adequately account for the observable characteristics of the visual experience. Central to this revolutionary approach was Alhazen's groundbreaking intromission theory of vision. For centuries, the dominant view, largely inherited from Euclid and Ptolemy, posited that vision occurred through emission, meaning the eye actively sent out rays or visual spirits that struck objects, allowing them to be perceived. This perspective suggested the eye was the active agent, projecting something outward. Alhazen, however, proposed a fundamentally different mechanism of vision occurred when light rays, originating from an external object, entered the eye. This placed the object and the light it emitted or reflected at the forefront of the visual process. The problem this addressed was profound. The emission theory struggled to explain phenomena such as the blinding effect of staring directly into the sun, or how we could see objects that were not illuminated. If the eye sent out rays, why would intense external light be detrimental, and how could unseen objects reveal themselves? Alhazen's intromission theory offered a more coherent explanation. He argued that objects themselves were the source of what we see, either by emitting their own light to flame, or by reflecting the light of a luminous source, like the sun. These rays, traveling from the object, then entered the eye. This simple yet profound shift in perspective had far-reaching implications. It meant that vision was a process of reception. The eye, in this model, became a sophisticated instrument designed to capture and process these incoming visual rays. The clarity and detail of our vision, he reasoned, depended on the precision with which these rays were gathered and focused. To substantiate this radical idea, Alhazen meticulously demonstrated its validity through rigorous experimentation. His methodology was a testament to his commitment to empirical evidence, a stark contrast to the purely philosophical or deductive reasoning that often prevailed. One of his most celebrated experimental demonstrations involved the camera obscura, a darkened chamber or box with a small hole in one wall. The problem he sought to explore was how an image of the external world could be formed within this darkened space. The emission theory provided an incomplete explanation for this phenomenon. Alhazen utilized the camera obscura to show that light, passing through a small aperture, would project an inverted image of the scene outside onto the opposite wall. He described how, if one were to view a brightly lit object, such as a candle or a window, through a small hole in a dark room, an image of that object would appear on the surface behind the hole. Crucially, this projected image was inverted. This inversion was a key piece of evidence supporting his intromission theory. If rays emanated from the eye, accounting for this consistent geometric inversion presented challenges. However, if rays traveled in straight lines from the object through the aperture, the geometry of projection naturally explained the upside-down image. Rays from the top of the object would pass through the bottom of the aperture and strike the top of the screen, and vice versa. His experiments extended to varying the size of the aperture. He observed that a larger opening allowed more light to enter, creating a brighter image, but at the cost of clarity, the image became blurred because rays from different points on the object would pass through different parts of the larger opening, converging at multiple points on the screen. Conversely, a smaller opening produced a sharper, clear image, though it was dimmer, as fewer rays were admitted. This observation was critical. It illustrated the principle that for a clear image to form, the incoming rays needed to be directed towards a single point. This foreshadowed the concept of focusing, a cornerstone of optics. Alhazen's approach was characterized by a systematic process of hypothesis, experimentation, and observation. He conducted a series of controlled investigations, carefully documenting his findings. He explored how the color and intensity of light affected the projected image, and how different materials interacted with light. His work with the camera obscura was a deliberate and controlled attempt to isolate the fundamental principles of how visual information travels from the external world to a receptive surface, whether that surface was the wall of a darkened room or, by extension, the retina of the eye. The significance of this experimental rigor cannot be overstated. It marked a profound shift in the scientific method. Alhazen actively sought to test theories against observable reality. His detailed descriptions of experimental setups and procedures allowed for replication and verification by others, a hallmark of true scientific progress. He established that the properties of light, its straight-line propagation, and its interaction with apertures were empirically verifiable facts. His intromission theory, supported by these methodical experiments, provided a far more satisfying and comprehensive explanation for vision. It accounted for why we see objects, why images are inverted in certain optical instruments, and the role of light intensity. By demonstrating that vision was a process of light entering the eye, Alhazen laid the foundation for all subsequent optical theories and physiological understandings of sight. His meticulous approach to empirical investigation set a precedent for scientific research that resonated through the centuries, influencing figures from Roger Bacon and Johannes Kepler to modern scientists. He demonstrated that understanding the natural world required careful observation and the systematic testing of hypotheses through demonstrable experiments. Alhazen's exploration of light extended far beyond its journey into the eye, delving deeply into the very nature of its interaction with the material world. He meticulously dissected how light behaved when it encountered surfaces and traversed transparent substances, laying down principles that remain foundational to our understanding of optics. One of the most significant contributions from his extensive work on light concerned reflection. The prevailing ideas of his era often struggled to articulate a precise understanding of how light bounced off surfaces. Alhazen, through rigorous observation and geometric reasoning, established the fundamental law of reflection. He demonstrated with compelling clarity that the angle of incidence, the angle at which a ray of light strikes a surface, is precisely equal to the angle of reflection, the angle at which it rebounds. This was a precise, quantifiable relationship derived from his experimental setup. He showed that the incident ray, the reflected ray, and the normal and imaginary line perpendicular to the reflecting surface at the point of incidence all lie within the same plane. This elegant geometric formulation provided a powerful tool for predicting and understanding how light would behave when encountering mirrors of various shapes. The problems of this time were to explain the formation of images in mirrors, the way light travels from an object to a mirror, and then to the eye, and why these images appeared as they did. Alhazen's law of reflection provided the essential mathematical framework to address these questions, explaining why a mirror redirects light in a predictable manner, allowing for the formation of virtual images and the visual perception of reflected objects. His investigations extended to curved mirrors, including spherical and parabolic forms, which were of immense practical interest for the development of optical instruments. He grappled with understanding how light rays from a single-point source would reflect from these curved surfaces and converge or diverge. This required a sophisticated application of geometry, particularly conic sections, to describe the paths of light. The challenge was to predict the focal points and the nature of the images formed, which depended intricately on the curvature of the mirror. Alhazen's application of geometric principles to complex shapes represented a significant advancement. He demonstrated how light rays parallel to the principal axis of a parabolic mirror converge at its focus, a principle foundational to the design of telescopes and searchlights. His work on spherical mirrors, though more intricate due to spherical aberration, offer detailed geometric descriptions of image formation, a crucial step toward comprehending how lenses and mirrors manipulate light for magnified or reduced images. In addition to reflection, Alhazen undertook a similarly meticulous study of refraction, the bending of light as it passes between transparent media. This phenomenon proved critical for understanding light's behavior when entering water, glass, or the atmosphere, directly influencing visual clarity and lens function. The challenges of his era included explaining the distortions and positional shifts observed when viewing objects through water or glass, and accurately predicting light's path through these media. Alhazen identified that the degree of bending depends on the properties of the two media and the angle of incidence. While he did not formulate Snell's law in its current trigonometric form, his empirical investigations yielded a profound understanding of the relationship. He observed light bending toward the normal when entering a denser medium and away from the normal when entering a less dense medium. His experiments involved measuring angles of incidence and refraction, establishing a proportional relationship between these angles, a proportionality later refined by scientists such as Willibrord Snell and René Descartes. Alhazen's approach to refraction was distinguished by its reliance on experimentation and geometric reasoning. He constructed apparatuses to measure the angles of light rays passing through glass, spheres, and other transparent objects. He meticulously documented the changes in apparent object positions when viewed through these media. This empirical foundation enabled him to construct a theoretical framework explaining the observed phenomena. He recognized that light speed alters as it traverses different media, a vital insight that anticipated later optical developments. His work on refraction proved especially important for comprehending light's behavior within lenses. Lenses are essentially shaped pieces of transparent material engineered to refract light in specific ways. This understanding proved vital for developing spectacles, telescopes, and microscopes, instruments that would fundamentally alter scientific observation and human perception. The enduring significance of Alhazen's research on reflection and refraction is substantial. His law of reflection continues to serve as a fundamental principle in geometrical optics, crucial for understanding light's behavior in a basic mirror and in the sophisticated optical systems found in advanced scientific instruments. The principles he established inform the design of nearly every optical device employing mirrors, encompassing telescopes, cameras, and lasers. Likewise, his groundbreaking studies of refraction established the foundation for lens development. The capacity to predict and manage light's bending is essential for correcting vision with eyeglasses, magnifying distant objects with telescopes, and observing minute details with microscopes. His thorough empirical methodologies and his dedication to mathematical description established a benchmark for scientific investigation that continues to inspire. He showed that light's seemingly intricate behavior could be understood through systematic observation, experimentation, and the application of precise mathematical principles, transforming optics from philosophical speculation into a rigorous scientific discipline. His contributions supplied the essential conceptual frameworks that allowed subsequent generations to build upon his achievements, leading to the advanced optical technologies we depend on today. Alhazen's explorations into light's behavior extended well past the foundational principles of vision and the characteristics of basic optical instruments. He tackled profoundly difficult geometric challenges, displaying an exceptional ability to apply mathematical precision to complex physical situations. The intellectual environment of his time wrestled with questions concerning how light rays interact with curved surfaces, particularly the intricate trajectories light follows when reflecting from mirrors. This presented a considerable obstacle to understanding how we perceive objects, especially when the geometry of the reflecting surface introduced complexities that resisted straightforward, intuitive explanations. A primary challenge that engaged Alhazen's sharp analytical intellect was what is now recognized as the problem of Alhazen, or the reflection problem. This geometric puzzle involved identifying a point on a spherical or elliptical surface from which light rays originating from two separate points would converge at a third point, the observer's eye. In simpler terms, given 2 points and a curved mirror, where must the observer's eye be positioned so that they can see both points after reflection? Or, conversely, given 2 points and an observer's eye, where on the mirror does a reflection occur? The latter formulation, finding the point on the mirror, proved particularly demanding. Consider the scenario of a spherical mirror. Light rays from one point, say A, travel to a point P on the mirror's surface, and then reflect towards the observer's eye, E. Simultaneously, light rays from a second point, B, also travel to a point P on the mirror and reflect towards the same eye, E. The problem is to determine the location of point P on the mirror. Alhazen approached this by recognizing that the angle of incidence equals the angle of reflection, a fundamental principle he had already established. However, Applying this principle to a sphere, where the normal to the surface varies, continuously transformed a straightforward geometric task into a formidable algebraic one. Alhazen's solution involved a sophisticated interplay of geometry and algebra, foreshadowing the development of analytic geometry centuries later. He translated the geometric conditions of the problem into algebraic equations. For a spherical mirror, he established that the locus of points P that satisfy the condition for a fixed point A and a fixed IE is a circle. However, the problem required finding a point P on this circle that also satisfied the reflection condition for a second point B. This led to the intersection of two circles, a problem that could yield up to 4 solutions, reflecting the various possible points on the mirror from which the observer could see both sources. The elegance of Alhazen's method lay in his ability to construct an equation that described the geometric relationships. He employed geometric constructions and theorems, including those concerning intersecting chords and secants within circles, to derive the required algebraic relationships. Specifically, he examined the distances between points A, B, and E, and point P on the sphere, connecting these distances through the law of reflection and the sphere's equation. This endeavor demanded a thorough comprehension of Euclidean geometry and the developing methods of algebraic manipulation. He successfully converted a problem of spatial relationships into one solvable by polynomial equations. The challenge of locating a point on a circle, where the sum of distances to 2 fixed points remains constant, defines the overlook Cassini. Alhazen's problem, conversely, involved the product of distances or ratios of distances, resulting in more intricate algebraic curves. His method for a spherical mirror, transforming geometric constraints into an equation of the 4th degree, represented a considerable accomplishment. He illustrated that such a problem could be simplified to finding the roots of a particular polynomial equation, a clear demonstration of his algebraic skill. Moreover, Alhazen broadened his investigation to elliptical mirrors, where the problem presented greater complexity. The set of points reflecting light from point A to point E on an ellipse forms a more elaborate curve. Identifying a point P on this curve that also fulfilled the reflection condition for a second point B necessitated even more sophisticated algebraic and geometric reasoning. His contributions to these problems highlighted a deep capacity for manipulating abstract mathematical ideas and applying them with exceptional accuracy to physical occurrences. The importance of Alhazen's solutions to his namesake problem is immense. He established a structured, mathematical approach for understanding reflection from curved surfaces, a challenge that had resisted simpler geometric solutions. His technique of translating geometric conditions into algebraic equations marked a pivotal advancement toward the creation of analytic geometry, a discipline that would profoundly transform mathematics and physics. The ability to describe geometric objects and their properties using algebraic equations, and conversely, to solve algebraic equations by visualizing geometric relationships, became the cornerstone of modern mathematics. The enduring impact of this work lies in its direct solutions and the methodology it exemplified. Alhazen's rigorous approach, his insistence on proof, and his ability to tackle complex problems with sophisticated mathematical tools set a precedent for scientific inquiry. The problem of Alhazen itself and its solutions continued to be studied by mathematicians for centuries, including luminaries such as Bono, Viet, and Descartes, who built upon Alhazen's foundation to further develop the field of analytic geometry. The problem's inherent difficulty and its rich mathematical structure made it a fertile ground for exploring new algebraic techniques and geometric insights, ultimately contributing to the broader development of mathematical understanding across diverse fields, from optics to mechanics. His meticulous investigations into these optical puzzles reveal a mind capable of abstract thought and a deep commitment to uncovering the mathematical order underlying the physical world. Alhazen's profound insights into the nature of light and vision, meticulously detailed in his Kitab al-Manazir the Book of Optics remained influential beyond the intellectual sphere of the Islamic Golden Age. The dissemination of this seminal work represented a critical juncture in the transmission of scientific knowledge, fostering a fertile ground for inquiry across different cultures and epochs. Its journey westward, primarily through Latin translations beginning in the late 12th and early 13th centuries, initiated a cascade of influence that would profoundly shape the trajectory of Western scientific thought, particularly during the transformative periods of the medieval scholarly revival and the burgeoning Renaissance. The challenges associated with integrating Alhazen's complex geometrical analyses and his novel experimental methodologies into the existing intellectual frameworks of medieval Europe were considerable. Scholastic traditions, while robust in their logical argumentation, often prioritized deductive reasoning from established authorities over empirical investigation. Alhazen, however, offered a compelling alternative, one grounded in meticulous observation and quantifiable results. His systematic approach to understanding vision, for instance, moved away from ancient theories that posited emission from the eye, instead demonstrating, through reasoned argument and experimental demonstration, that vision occurs when light travels from the object to the eye. This fundamental shift required a reorientation of scientific practice, a move towards a more inductive and experimental paradigm. The impact of the Book of Optics became increasingly evident in the work of scholars who engaged directly with its translated texts. Roger Bacon, the 13th century English philosopher and Franciscan friar, stands as a pivotal figure in this intellectual lineage. Francis Bacon, deeply impressed by Alhazen's empirical rigor and mathematical sophistication, explicitly acknowledged his debt to the Arab scholar. He adopted and adapted Alhazen's optical experiments, extending them and integrating them into his own broader philosophical and scientific investigations. Bacon's own writings on optics, such as his Opus Majus, clearly echo Alhazen's principles, particularly in the emphasis placed on the role of experimentation in validating theoretical propositions. He recognized the power of Alhazen's methodical approach, seeing in it a pathway to a more reliable and verifiable understanding of the natural world, a departure from reliance on purely speculative reasoning. Bacon's advocacy for an experimental science, informed by Alhazen's example, laid crucial groundwork for the eventual development of the scientific method. The influence continued to ripple through subsequent centuries. Johannes Kepler, the German astronomer and mathematician of the late Renaissance and early Baroque periods, inherited this tradition of empirical inquiry, further building upon Alhazen's optical foundations. Kepler's groundbreaking work on vision, culminating in his treatise Astronomie pars optica, or the optical part of astronomy, in 1604, directly addressed many of the problems Alhazen had explored. Kepler's revolutionary understanding of how the eye functions as an optical instrument, forming an inverted image on the retina, was a direct descendant of Alhazen's meticulous analysis of how light rays converge. Kepler's mathematical treatment of refraction and his formulation of the laws governing the intensity of light, for example, owe a significant debt to Alhazen's pioneering geometrical optics. He engaged with Alhazen's geometrical proofs and his detailed descriptions of experiments, extending them with his own advanced mathematical tools and astronomical observations. Kepler's ability to synthesize optical theory with physical phenomena, particularly in his work on planetary motion, demonstrated the enduring power of Alhazen's empirical and mathematical synthesis. The transmission and assimilation of Alhazen's ideas also played a significant role in the development of analytic geometry, a field that would fundamentally alter the landscape of mathematics and physics. Alhazen's optical problems, such as the famous Alhazen's problem concerning the reflection of light from a spherical surface, required sophisticated geometric constructions and algebraic solutions. This problem, which asks to find the point on a reflective surface from which light emanating from one point will reflect to another, involves finding the intersection of a circle and a hyperbola. The algebraic formulation of this problem, which leads to a quartic equation, provided a challenging yet rewarding area for mathematical exploration. Later mathematicians, including the French algebraist François Viet and, most notably, René Descartes, engaged with these geometric challenges. Viet, in his work on algebraic notation and methods, developed tools that facilitated the solving of complex equations, making problems like Alhazen's more tractable. Descartes, in his own seminal work La Géométrie, famously unified algebra and geometry, demonstrating how algebraic equations could be used to describe geometric shapes and vice versa. Descartes' engagement with Alhazen's specific optical problems occurred through the lens of his own developing system, and the intellectual lineage is clear. The very act of translating geometric problems into algebraic equations, a cornerstone of analytic geometry, found a significant impetus in the kinds of complex geometric puzzles that Alhazen had posed and explored. The rigorous analytical approach required to solve these optical conundrums provided a fertile testing ground for the emerging power of algebraic methods in geometry. The enduring relevance of Alhazen's contribution lies in the specific solutions he provided to optical puzzles and in the very methodology he championed. His unwavering commitment to empirical verification, his insistence on constructing experiments to test hypotheses, and his sophisticated use of mathematics to describe and predict natural phenomena established a paradigm that would become the bedrock of modern scientific inquiry. The problems he tackled and the elegant, mathematically grounded solutions he devised served as exemplars for generations of scientists. His work provided a crucial bridge between ancient Greek geometric traditions and the emergent empirical sciences of the Renaissance and beyond, demonstrating that the pursuit of knowledge required a harmonious interplay of observation, experimentation, and rigorous mathematical reasoning. The intellectual threads woven by Alhazen's Book of Optics thus extended far beyond the field of vision, subtly but powerfully shaping the very way science itself was conducted, paving the way for the intellectual revolutions that would soon follow. Alhazen's intellectual legacy resides profoundly in the integrated approach he forged, a synthesis of empirical observation, meticulous experimentation, and sophisticated mathematical analysis that redefined the very practice of scientific inquiry. His unwavering commitment to grounding theoretical propositions in verifiable evidence established a paradigm that would resonate through the ages, becoming a cornerstone of modern scientific methodology. The intellectual threads woven by Alhazen's Book of Optics extended far beyond the elucidation of vision. They subtly yet powerfully shaped the trajectory of scientific thought, offering a compelling blueprint for how to investigate the natural world. The problems Alhazen confronted were deeply embedded in centuries of philosophical speculation. Prior theories of vision, largely inherited from Greek thinkers, posited an emissive theory, suggesting that the eye projected rays outward to perceive objects. This framework, while elegant in its geometric articulation, struggled to account for numerous observable phenomena, such as the apparent size of objects at different distances or the precise manner in which light interacted with surfaces. Alhazen's departure from this established orthodoxy was revolutionary. He posited, instead, an intromission theory, arguing that light emanated from objects and entered the eye. This fundamental shift, seemingly simple, unlocked a cascade of new questions and avenues of investigation that had been previously obscured. His unique solution lay in his methodical, almost forensic, dissection of the visual process. Alhazen meticulously designed experiments to test his hypotheses. He employed chambers of varying sizes, apertures, and materials, observing how light traversed these spaces. His famous camera obscura experiments, where light passing through a small hole in a darkened room projected an inverted image of the outside world onto a screen, provided compelling visual evidence for the rectilinear propagation of light. This was an active interrogation of nature designed to elicit specific, measurable responses. He demonstrated his findings. He meticulously documented the results of these experiments, detailing the conditions under which they were performed and the precise observations recorded. The mathematical rigor Alhazen applied to his optical investigations further distinguished his work. He utilized geometry, the established language of precision, to describe the paths of light rays. His analysis of reflection and refraction, for instance, was quantitative. He formulated principles that accurately predicted the angles of incidence and reflection, and he explored the complexities of refraction through different media, laying groundwork for later developments in understanding lenses and optical instruments. His treatment of the laws of reflection demonstrated a profound understanding of geometric relationships, showing how light rays bouncing off a surface adhere to predictable patterns. The enduring relevance of Alhazen's work is undeniable. The camera obscura, a direct product of his experimental approach, became a foundational tool for artists and scientists alike, its principles echoing in the development of the photographic camera and modern imaging technologies. His insights into the nature of light and vision directly influenced the work of later European scientists, including Kepler and Descartes, who built upon his foundations to further unravel the mysteries of optics. The very concept of empirical verification, the bedrock of the scientific method, finds a powerful early champion in Alhazen. His insistence on testing hypotheses through controlled experiments, rather than relying solely on deductive reasoning or philosophical authority, marked a pivotal moment in the evolution of scientific thought. Alhazen's contribution was a comprehensive reorientation of scientific practice. He demonstrated that understanding the natural world required a disciplined and systematic engagement with it. His meticulous observations, coupled with his sophisticated mathematical framework, provided a tangible and reproducible method for exploring complex phenomena. This integration of empirical evidence and mathematical description became the hallmark of successful scientific endeavor, a testament to his profound influence. He refined the very instruments of scientific discovery. The intellectual lineage tracing from Alhazen is rich and far-reaching. His work on tonic sections, for instance, further solidified his mathematical prowess and contributed to the broader understanding of these fundamental curves, which would later prove essential in celestial mechanics and other fields. His explorations into geometry and algebra provided the essential tools and conceptual frameworks that enabled subsequent generations to tackle increasingly complex problems. He offered a compelling model for how abstract mathematical principles could be applied to illuminate concrete physical realities. Alhazen's methodical approach to problem-solving provided a departure from the more speculative, philosophical traditions that preceded him. He embraced complex questions with a spirit of empirical inquiry. His investigations into the properties of light, the mechanics of vision, and the behavior of optical phenomena were characterized by a persistent questioning and a relentless pursuit of demonstrable truth. This dedication to empirical validation, to building knowledge brick by painstaking brick through observation and experiment, represents his most significant and lasting contribution. The intellectual revolution initiated by Alhazen's Book of Optics was a steady, illuminating flame. He provided a robust methodology, a clear demonstration that the pursuit of knowledge demanded a disciplined engagement with the physical world. His legacy is etched in the specific discoveries he made concerning light and vision, and in the enduring principles of scientific investigation that he championed. He showed that the path to understanding lay through careful observation, rigorous experimentation, and the elegant precision of mathematics, a testament to a mind that fundamentally reshaped how humanity perceived both the universe and its own capacity to comprehend it. His commitment to empirical truth serves as an enduring beacon, guiding the scientific endeavor through centuries of exploration and discovery.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.